Okay, welcome one, welcome all. How are you guys today? Um, I wanted to pick up where we left off last time on Monday. Um, Monday's lecture was really long, and unfortunately, or fortunately, depending on your perspective, today's probably also going to be a little on the longer side. Um, so definitely remember to take breaks. I hope that you guys are staying well. So let's see. Last time we talked about the finite square well. In this case, the the potential as the 1D potential as a function of x goes as uh, 0 if you're outside. So if your x is less than minus a, or if your x is greater than a, and it took on a value of minus v naught, where v naught is some constant, positive constant uh, between minus a and a. And really we did this just so that we could set the floor down here, right? And it makes solving in the regions x less than minus a and x greater than a little easier. Um, and and it doesn't cause uh, any changes to the physics of the problem. So last time we looked at bound states where E was less than 0. So in other words, the energy available to the particle um, is between minus V naught and 0. So classically, this particle is entirely uh, to be found in region 2. Um, and so we went about solving this, and in the interest of time, I'm not going to go through this again entirely, but uh, we looked at 3 regions, regions 1, regions 2, and regions 3. Uh, and in region 1, where we started, the Schrodinger equation, time-independent brand, uh, v goes to 0, right? That's what we said here. And so the Schrodinger equation just becomes minus h bar squared over 2m d squared psi dx squared is equal to e times psi, which we could multiply across uh, multiply both sides by minus 2m over h bar squared to get to d squared psi is d squared psi dx squared is equal to kappa squared psi, where kappa was defined to be minus 2me over h bar squared, all of that under the square root, or minus 2me under the square root divided by h bar, right? Same difference. Um, and we had this general solution that that psi goes as a e to the minus kappa x plus b e to the kappa x. Um, and this first term represented a problem for us physically because it would blow up as x approached minus infinity, and so we solved that just by setting a equal to 0 and getting psi goes as b kappa x. In region 3, we could perform a similar operation and get uh, have the opposite problem though, right? This time the solution would blow up as x approached infinity, and so we set uh, the plus kappa x term coefficient g to 0. And we wound up within region 3 that psi of x is equal to f e to the minus kappa x, right? So differs. In region 1, we had psi went as b e to the kappa x. In region 3, we had psi went as f e to the minus kappa x. And in between, um, we had kind of we still had to account for uh, the non-zero potential. So the potential was minus v naught in between. And so first add v naught psi to both sides, then multiply both sides by minus 2m over h bar squared. And we had that d squared psi dx squared is minus l squared psi. where L takes on the value square root of 2m quantity E plus V naught and quantity in the numerator, all of that divided by H bar in the denominator. This had solutions of psi is equal to C sine Lx plus D cos Lx. But note that we could have also written this as Pe to the ILX plus QE to the minus ILX, right? And that wouldn't have that would have also been a valid trial solution, and we would have just had to solve for the coefficients P and Q instead. I'm going to put a pin in that because we're going to take a similar approach to that in a few minutes. But then remember that our steps were we imposed continuity of psi and d psi dx at the two boundaries between region 1 and 2 and between regions 2 and 3. So those are at x's minus a and plus a respectively. We had this idea that since the potential function is even, the solutions to the Schrodinger equation had to be either purely even or purely odd. We solved for the even attempt and got such. And then we looked at scattering states. Or I guess that's where we are today. Sorry, all the days are blending together for me. In a scattering state, E is greater than 0. So in the case that we apparently looked at last time, E was less than 0, which but greater than minus V naught, right? So it was bound, right? Classically bound. This time we're looking at the finite square well, so same description of the potential, but this time the energy is up here, right? The energy of the particles that we want to examine is up here. So I think that probably satisfies, or at least when we're done, will have satisfied all of the possibilities, right? The energy is either greater than 0 or less than 0. Right? So again, region 1, nothing has changed. For the potential, right? So in region 1, the potential is 0. Up here in region 1, the potential is 0. There is a slight difference computationally, though, right? Because this time we still have the minus h bar squared over 2m times d squared psi dx squared plus 0 is equal to e psi, right? Because v is 0. But we get that d squared psi dx squared is equal to minus 2me over h bar squared psi. This time, since e is greater than 0, this is the negative of a positive constant times the original function, right? And so this time we get psi of x is equal to ae to the ikx plus be to the minus ikx, where again k is square root of 2me over h bar squared, or in the numerator square root of 2me and the denominator h bar. Note that the plus e to the plus ikx term represents a wave traveling from minus infinity towards plus infinity, and the be to the minus ikx, the e to the minus ikx term represents a wave traveling from plus infinity towards minus infinity, right? And so I'm going to keep both of these terms, and what I'm going to assume is that I the I the wave is heading rightwards, right? It's heading from minus infinity towards plus infinity. In other words, um, the the particle, the wave, however you want to think of this, is coming from this direction and in region 1 approaching region 2. And what I want to explore is when it encounters this boundary between when it encounters uh, this obstacle, right? This well, some of it will scatter back, some of it will transmit forwards. That's how I want to think of this. And so in region 2, we have minus h bar squared over 2m d squared psi dx squared minus v naught psi is equal to e psi. This time we have d squared psi dx squared is equal to minus 2m over h bar squared times quantity e plus v naught and quantity times psi. E and absolute v naught are obviously both positive because we said that e is greater than 0. And so this is obviously positive. 2m over h bar squared is positive. And so we have a negative times the product of two positive numbers is ultimately negative. And so we have that the second derivative is some negative constant value multiplied by the original function. We've seen this solution before. It is sines and cosines. Again, we could write this in terms of e to the ix plus e to the minus ix, or e to the some coefficient times e to the ilx plus some coefficient times e to the minus ilx if we wanted to, but for now I'm just going to leave it as such. Yay. Convince yourself that if you took the second derivative of this, you would get this thing in the right. Pause the video and double check. In region 3, it's a lot like region 1, right? Again, we have the potential 0 out here. So we have minus h bar squared, d squared psi dx squared plus 0 is equal to e psi. D squared psi dx squared is minus 2me over h bar squared times psi. Psi is equal to fe to the ikx. Why didn't I keep the g term this time? Well, I wanted to assume, again, that there is this instant wave traveling rightwards with coefficient a. There is this reflected wave traveling leftwards. And then there is the part of the wave, the part of this instant wave that is actually transmitted with coefficient f. What I've assumed here is that there is no wave incoming from positive infinity towards this barrier. That the structure here is that we are sending this wave packet, this wave in from negative infinity towards the origin, and some of it transmits, some of it reflects. We're not sending something in from plus infinity towards the well. And again, we'll impose continuity at minus a. So we take region 1 solution and insist that it equals to region 2 solution where x is set equal to minus a, and we get that. And then we take the first derivative of the psi in region 1 and the psi in region 2 and insist that that must be equal, they must be equal to one another at x equals to minus a, and I get this, which I called equation 2. We could do the same thing at x equals a, but this time we're using the solutions from region 2 and region 3. And so we're going to take this region 2 solution and insist that it equals this region 3 solution at x equals a, and we get equation 3 and equation 4. Pause the video here and make sure that you have something similar. We have 4 equations, which is a good thing because I count 1, 2, 3, 4, 5 unknowns. That's going to be a little tricky for us, right? But let's see what we can make of this. So what we're going to do is we're going to solve 2 of the equations to eliminate C and D, and we'll use the remaining 2 equations to solve for B and F in terms of A. So what we're going to do is we're going to solve for the coefficients B and F in terms of this instant wave. I'm going to cheat just a little bit, and I'm not actually going to do this because it is in my my notes sitting next to me right now, and it is more than 1 page, and it would just, I think, not translate very well to this format. So if you want to see how to do this, please come to office hours and I'll go through it with you. But it's it is a long derivation. But if we do that, we get the b is equal to I times sine of 2LA divided by 2KL multiplied by L squared minus K squared, and that multiplied by F. And then F is equal to e to the minus 2IKA times A divided by the denominator cosine of 2LA minus I times K squared plus L squared over 2KL multiplied by sine of 2LA. So this guy, right? Yay? How does this help us? Well, if I wanted to think of what fraction of the wave is actually transmitted, well, what we said is that F represents the coefficient of the transmitted portion, and A represents the coefficient of the instant portion. And so the ratio of those is, in some sense, the fraction of the original wave that is transmitted. The if we took B over A, that would be the fraction of the wave that is reflected, right? So use the same terminology. And so since this is written in terms of A, this is just e to the minus 2IKA over cosine 2LA minus I sine 2LA over 2KL multiplied by K squared plus L squared. We could multiply top and bottom by 2KL and get that T is equal to 2KL times e to the minus 2IKA divided by 2KL cosine of 2LA minus quantity K squared plus L squared end quantity times I sine 2LA. That probably seems painful, and I am copying this because we're going to come back to this. I know that you're probably gonna have to pause the video here for all of your cheering, but but this is going to be useful to us in a few minutes. So remember uh, that the wave functions themselves are not the probability of locating the particle. It's the square of the wave functions, right? It's the psi star psi. So if we wanted to look at the probability of transmission, we'd look at t squared. And so that's just taking this term and squaring it. Um, and that you can see, so the a squared over a squared cancels, you just get 1 over that stuff. That's kind of a bear, right? That doesn't seem so fun. And so the way that this is often examined is the inverse of t squared. And that is just all of this bracketed stuff, right? Cosine squared of 2LA plus k squared plus L squared squared over 4k squared L squared sine squared of 2LA, right? This guy is more often examined. And let's see if we can simplify this a little. So note that I I can rewrite this second piece, this k squared plus L squared squared over 4k squared L squared sine squared 2LA as I as k squared plus L squared squared over 4k squared L squared minus 1 plus 1 times I sine squared of 2LA. Here, let me write that out for you. So if you have some constant, in this case, k squared plus L squared squared over 4k squared L squared times sine squared of 2LA, well, instead of 2LA, I'm going to call that theta. Instead of this thing out front, I just called it A. So, so if you have A squared sine squared theta, you could rewrite that as A squared minus 1 plus 1 times sine squared theta, right? If I subtract 1 from it and I add 1 to it, it's still A squared, right? Hopefully that's okay. Convince yourself that this is true. If we do that here, something interesting happens. Oops. Instead of k squared plus L squared squared over 4k squared L squared, we get k squared minus L squared squared over 4k squared L squared plus, and I, right? And so I can rewrite this term as this. So I can take out a sine squared of 2LA. I don't know whether you really do this when I suggest that you stop and convince yourself that something is true, but here is probably a good point. Start with this and make sure that you believe that this is true, that this is equal to this. But if you do that, note that you have cos squared of 2LA plus sine squared of 2LA right here, and cos squared plus sine squared is 1, right? And so we could just replace this with 1 plus, and now I'm going to go back to our definitions of what we mean by K and L. So this K squared term is just 2me over h bar squared. This L squared term is just 2m times e plus v over h bar squared, right? So we have this thing in parentheses up here just becomes this, and it's still squared. And then in the denominator, we have 4 times, well, k squared is still 2me over h bar squared, L squared is still 2m times e plus v naught over h bar squared, times sine squared of 2LA, sine squared of 2LA is take this and multiply by I by 2a, and you'll get that, right? This probably still isn't seeming that much simpler, but if I take 2me and I subtract from it 2me plus v naught, right? I get minus 2mv naught, the 2me parts go away, over h bar squared, still have to square it, over 4 times 2 times 2 is 4, m times m is m squared, e times e plus v naught is right there, h bar squared is here to give h bar to the fourth, and then still sine of all that junk, right? How is this helpful? Well, a lot of this clears, right? When I square this, this minus sign goes away. But I'm also going to get 4m squared over h bar to the 4, and notice that there is a 4m squared over h bar to the 4 here, and so those pieces are going to go away. And what I'm left with is the inverse of sorry about that. The inverse of I can't win. The inverse of t squared is now 1 plus v naught squared over 4e times e plus v naught times sine squared of 2a over h bar times the square root of 2m e plus v naught. What I want to point to is when this well will just let the wave pass straight by as though the well wasn't there. That will be true when t squared is equal to 1. But when t squared is equal to 1, the inverse of t squared is also equal to 1, right? And so, so I want to know when is the inverse of t squared equal to 1. Well, it'll equal 1 anytime the rest of this goes to 0. This prefactor can't go to 0. And so what we need is sine squared of the argument to go to 0. And so that will happen if the argument of this sine is 0, right? Or sine squared is 0. It'll also happen anytime this stuff in parentheses is equal to some integer multiple of pi. And so, so the argument being 0 is kind of a boring case, right? That speaks to the well having no width. But the interesting case is when this piece is an integer multiple of pi. Because then we can say that 2a over h bar times the square root of 2m times the quantity e plus v naught end quantity is equal to n pi, we can multiply both sides by h over 2a, h bar over 2a, sorry, and then square both sides, and then divide both sides by 2m, and we'll get the following, that E plus V naught is equal to n squared pi squared h bar squared over 2m times quantity 2a and quantity squared. But 2a, note, is the width of this well. And so we could say that E plus V naught is equal to n squared pi squared h bar squared over 2ml squared, where n is some integer. Again, we have these quantized energy levels where the wave passes straight by without getting reflected at all. All of it passes straight through. The other interesting thing here is that note that these are the same energies that we saw for our square well, right? So there's, you know, some interesting thing that's going on here. Hopefully that's not terrible. Go back and work through this. The other thing that I would suggest is this might be a good point to take a break. I normally try to have our lecture videos be about 20 to 30 minutes long at a time. The one that we did on Monday, I think, was well over an hour. And I think that this one is probably going to do that also. So, so maybe get up, stretch around, uh, have a Milky Way candy bar, and then pick up in a second. All right, so hopefully you are well rested. Mind is all set to go. This time I want to turn our well upside down, and I want to look at scattering from a finite step. And specifically, I want to look at the case where E is less than V naught. So in other words, I want to look at the case where the energy of this particle is below the step. And again, I'm going to have it start out at minus infinity, head towards the well, and classically, there is no chance this thing passes, right? It doesn't have enough energy to overcome the barrier, and so it should reflect. Quantum mechanically, what we're going to see is that's not necessarily the case. This is what we call quantum tunneling. There is some chance that this particle can pass through this well, even though classically it shouldn't have enough energy to do so. So I want to look at the case of E less than V naught. So hopefully this is okay. Again, I have defined the potential to be 0 for x less than minus a, and 0 for x greater than x equals plus a, and this time I'm just going to let it be plus v naught between minus a and a. So commit this to memory, and we'll and put it in your notes, and we'll proceed. This starts out in very familiar territory. Region 1, minus h bar squared over 2m d squared psi dx squared, plus 0 is equal to e psi, minus d squared psi dx squared is equal to minus 2me over h bar squared times psi. And again, we've got psi of x is equal to a e to the ikx plus b e to the minus ikx, where k is radical 2me over h bar. This time I'm going to take, so you'll remember that this is the same solution we had in region 1 up here, right? which makes sense because the potential is the same out here, right? This time I'm going to take a slightly different tact than the one we've previously done. We could have done this before. In fact, you may be angry with me for this, but it would have made some of the math a little easier for us. But this time, the part of the wave that's traveling rightwards, I want that to be the instant wave, and I'm just gonna scale that to have a prefactor of 1, right? And so I'm just gonna let that be 1 times e to the ikx. And then the reflected piece, I'm even going to name that coefficient r just so that uh, we can see something a little more natural as far as uh, mnemonic devices. And so this you can think of as representing the wave traveling from minus infinity towards this finite step. And this you can think of as the portion of the wave that gets reflected back towards minus infinity. Yay? But it's still basically the solution. I'm just insisting that uh, the wave starts out at minus infinity and comes towards the boundary. And I'm just saying that I just renamed B to be the reflected component. And we can do this with basically no loss of generality. This works because we're looking at ratios and we don't I'm not going to bother trying to normalize this. So region 2, we have minus h bar squared over 2m d squared psi dx squared plus v naught psi is equal to e psi. So I can subtract the v naught psi to both sides, and then multiply both sides by minus 2m over h bar squared, and we get that d squared psi dx squared is equal to minus 2m over h bar squared times e minus v naught times psi, which is just flipping the order of e and v naught, the same as 2m over h bar squared times the quantity v naught minus e and quantity times psi. And we can write this, so note here that the way that we've said this, v naught is greater than e, and so v naught minus e is a positive value. We've seen solutions to this before. Psi of x is just equal to ce to the kappa x plus de to the minus kappa x, where kappa is just going to be the square root of 2m times quantity v naught minus e and quantity over h bar squared, or in the numerator, square root of 2m quantity v naught minus e and quantity, in the denominator, just h bar. Yay? We're happy with this. Convince yourself that you're happy with this before you move on. Okay, so region 3 looks a lot like region 1, right? If we come back here, the potential is the same, right? We're dealing with presumably in our simple model, the potential is symmetric about the origin. So this time, x greater than a, minus h bar squared over 2m d squared psi dx squared plus 0 is equal to e psi. D squared psi dx squared is minus 2m e over h bar squared times psi. Just like in region 1, I named the coefficient r for reflected. Here, I want to name the coefficient t for transmitted. And I'm doing the same thing that we did in our last example, where I'm assuming that there isn't a wave coming from infinity towards this step, and so I'm only keeping the rightwards traveling piece, right? So the general solution would also carry an e to the minus ikx term. I'm just omitting that entirely, and I'm assuming that there isn't any component of coming from positive infinity back towards the boundary. So I'm only going to keep the rightwards traveling piece. And again, k is still equal to radical 2me over h bar, just like it was up here. Yay? Okay, so much as before, we're going to say impose continuity of x at minus a, of psi, and of the first derivative of psi with respect to x, and we get equations 1 and 2. If we do the same at x equals plus a, insisting upon continuity of psi between region 2 and region 3, whereas remember up here we were imposing continuity of psi between regions 1 and regions 2. We do the same between region 2 and 3, we get these two equations, which I named 3 and 4. You probably right now are hoping upon hope that I'm going to actually go through all the math, because I know you love watching that, but I'm not going to. Instead, what I'm going to point to is that this is the exact same thing that we've been doing with the, so if I come back up to here, right, it's the exact same thing, except that it doesn't, there's no L in the one we're doing now, right, whereas there was for our finite square well. But these equations are identical, except that L is turned into I times kappa. Yay? Um, the joy of this is that it means that we can template our solution from before. So remember that previously, way up here in our finite square well, we had gotten to this statement, right, which I have just copied and pasted to here, right? So that is just that thing. And what I'm telling you is everywhere in that solution that you see an L, because equations 1, 2, 3, and 4 here are the same as the 1, 2, 3, and 4 above, except that uh, some minor differences in the way I named the coefficients. But we can just take those, since the equations 1, 2, 3, and 4 are the same, just with again minor differences in the way I named the coefficients. And maybe if I had planned this out better, I wouldn't have done that, because then it would have seemed even more explicitly true. But um, it is still totally valid. Everywhere in this old solution that we had an L, we can just replace it with an I times a kappa, because that's really the only difference between these 1, 2, 3, and 4 equations for the finite step compared to the finite well. You're just substituting L for I kappa to get these sets of equations. Yay? And so we can do the same thing in our solution. If you do that, then here's where I will leave it to you to decide whether or not you actually want to do this. If you take all of these and swap out I kappa for each of the L's, and then you remember your hyperbolic trig identities that and you actually don't even need that one. that sine hyperbolic sine of z is just equal to minus I sine of iz, and hyperbolic cosine is just equal to of z is just equal to cosine of iz. If you swap out L's, every L you see for I kappa, then this one turns into an I kappa, this one turns into an I kappa, this one turns into an I kappa, this one turns into I squared kappa squared, and I squared is -1, and this one turns into I kappa. If you do that, then you can get to this equation by also applying these hyperbolic trig identities. If that interests you, you can pause the video and try and do so right now. And regardless, hopefully you're back. Let's see. So then, in this case, the transmission probability should just be t squared, right? T star t, which is t squared. If you do that, well, the numerator squares nicely to 2k kappa in quantity squared. The denominator will take a little bit of work, but you can demonstrate using other hyperbolic trig identities that you can rewrite this as this if you square it, right? Hopefully that doesn't wind up being too terrible. What I would tell you is then if you keep only leading terms, you can simplify this so that, well, you would get this in the numerator. I know because I just did this. And then in the denominator, you get an e to the 4 kappa a term, e to the -4 kappa a term, a -2 and a minus 16e times quantity v naught minus e term. Basically, if you only keep the leading term, it looks like this. So it tends towards this if kappa is significant. And remember, we defined kappa as 2m I times v naught minus e over h bar squared under the square root. So we can we can just ignore this coefficient out front and say that t squared is approximately e to the -4 kappa a. This is a really rough approximation, right? This was already an approximation, and now I'm even dropping this coefficient out front, but usually the exponential is going to beat some multiplied constant, although it is going to scale it, right? So So bear in mind that this is a really and truly rough approximation. But I can write e to the minus 4 kappa a as e to the minus 2 kappa times 2a, right? Just split the 4 into minus 2 and 2, or minus 2 times 2. And we can, and I'm not going to go through the math here. We can write this as equaling e to the minus 2 integral from minus a to a of our kappa value, right? Where'd that go? Right there. Dx. Yay. And so the thing that the reason that I didn't show all of the math is that I don't want to bury the lead. Um, the important thing about however you want to look at the solution, any of these, right, is that it's not necessarily zero, right? It might not be big, right? E to the minus 2 kappa I 2a, right? Basically, wow, I apologize if anyone's getting dizzy from all of that. Let's put this up here. What this means is there's some probability of transmission, right? Note that it goes as it's an exponential decay, right? It's decaying uh, as far as kappa goes, right? And remember, kappa is in some sense related to how much bigger V naught is than E, right? So if V naught is way bigger than E, kappa is big, right? So if either V, sorry, if either V naught or E or both goes up, then uh, then kappa gets big, right? So if V naught gets bigger but E stays the same, kappa gets big. If V naught stays the same and E gets smaller, kappa gets big. If V naught goes up and E goes down, kappa gets really big, right? And a wider well means that 2a goes up. Since this is e to the minus 2 kappa times 2a, if kappa gets bigger or 2a gets bigger, the likelihood, this probability of transmission goes way down, right? It drops exponentially. Um, just um, to put kind of a point to this, um, the what color haven't I used? How about that one? The probability of transmission drops exponentially. But it's not zero, right? So if I make this this step narrow enough, or if I make V naught so that it's not way bigger than E, there is definitely a non-zero probability that the particle can go from region 1 to region 3. Classically, that can't happen. In quantum mechanics, though, it is absolutely possible for this particle to tunnel from region 1 to region 3. Okay, so, but wait, there's more. Not a whole lot more. So, uh, classically, we have an ideal particle can be localized, and localized completely. We can know where the particle is. Um, but now that we're describing the probability of finding the particle as being uh, described by psi squared, in quantum mechanics, we're going to now treat a particle as uh, a superposition of many, many, many wave functions that produces uh, a localized uh, packet of wave, right? And so this is what we're going to mean by a particle in in quantum mechanics. Uh, it is localized by virtue of how narrow this wave packet is described. And remember, psi squared is representative of the probability of finding the particle, right? And so this is going to get still steeper. Okay, so let's just have a brief rehash, right? So we have that E is equal to HF, and uh, so DEDF should just be equal to H, but that means that delta E should equal H times delta F. Yay? Right? So if we have E equals HF, then delta E delta F should just equal H. So delta E should equal H times delta F. Similarly, we have that P is equal to H over lambda, um, and so lambda should be H over P, but that means that delta lambda should be H times delta P over P squared. I dropped a minus sign here, right? But if lambda is H over P and you took d lambda dp, you would get minus H I over P squared, um, which tells us that delta lambda should be minus H delta P over P squared, but I just care about the magnitude. So if it makes you happier, put absolute value signs in your notes. Um, Now, here, imagine that we have some standard clock for measuring how many wave crests pass some fixed point per unit time. You could, I don't know, use some oscillator that produces waves whose frequency we're going to compare against. Um, if we let these two waves interfere and produce beats, then the number of beats per unit time is equal to the difference between the two waves' frequencies. So if you have no beats, that means that uh, the frequency of your experimental reference is the frequency of the wave in question. Um, if we wanted to make 100% sure that the reference and the wave under observation really had the same frequency, um, well, what we're doing is we're waiting until we hear a beat, right? If we never hear a beat, then we know that uh, that the frequency of our reference is the same as the frequency of the wave. So how long would we have to wait in order to make sure that they're the same? Well, you'd have to wait forever, right? And so the question becomes, what's our uncertainty if we measure beats from our wave and our reference over some finite time delta t? Well, um, we could take a conservative approach here to make sure that if anything, we're overestimating our our uncertainty. Um, and there, the conservative approach would be to say, well, we would expect to get one beat every delta t only if the beat has a period of delta t or smaller. And so from that, we could argue uh, that delta t times delta f would have to be greater than or equal to 1, right? Another way of saying that is uh, 1 over delta t has to be less than or equal to delta f. Hopefully that's okay. So if you're comfortable with this idea that delta t times delta f has to be greater than or equal to 1, well, we already have a statement for what we mean by delta f. Delta f is just going to be delta E over h. We also, um, so we could sub that in, right? That instead of delta f, we could plug in delta E over h, and then we would have delta E over h times delta t has to be greater than or equal to 1. We could multiply h across to both sides, and we would get delta E times delta t has to be greater than or equal to h. Now, for completeness, if we were looking at root mean square rather than h, we would say h over 4 pi. Um, and in fact, that's the approach that I'm going to take without further explanation. But put a pin in this because this is going to be important to us. We also have this statement that uh, from your physics 130 days that delta x is equal to v average times delta t, right? And let's assume that v is constant, so delta x is just equal to v delta t. We could use this and say uh, that delta t has to be greater than or equal to 1 over delta f. Um, and in so doing, then we get, if you plug in that for delta t, you get that delta x has to be greater than or equal to v over delta f. Yay? Um, so if we have this statement, then again we can uh, uh, we also have our statement of wave speed, that v wave is equal to f lambda. And so if we take our differential idea that we used previously, we could say that f is equal to v over lambda. I don't have to be quite this lazy. We could say that f is equal to v over lambda, and so df d lambda would just be uh, equal to v minus v over lambda squared. And so we could say then that delta f, throwing away the minus sign again, uh, just absolute value, right? Delta f is equal to v delta lambda over lambda squared, right? It's just taking the derivative of this with respect to lambda. The delta f is just equal to v delta lambda over lambda squared. And so here we have that delta x is greater than or equal to v over delta f. If we plug in what we now mean by delta f, we can say that delta x has to be greater than or equal to v times lambda squared over v times delta lambda. The v's cancel, and what we get is that delta x times delta lambda has to be greater than lambda squared, right? That's just this statement. But delta lambda times delta x, well, previously we had said that delta lambda was just h times delta p over p. And so if we sub in for delta lambda this statement, Um, sorry, I'm trying to fit this all in one screen, and it really doesn't want to. That if we sub in for delta lambda this equation, we get that h times delta p over p squared, uh, delta x has to be greater than or equal to lambda squared, and uh, multiplying across, we get uh, delta p times delta x has to be greater than or equal to lambda squared times p squared over h. But if you remember way back here, lambda times p is what we meant by h. And so this is really the same as having an h squared in the numerator, such that delta p delta x has to be greater than or equal to h. And again, if we were doing this for root mean square instead of the more simple way that I've approached this, you get h over 4 pi instead of just h. And so here, I remind you that h bar is just h over 2 pi, so h over 4 pi is h bar over 2, and so we get to what we will call the Heisenberg uncertainty principles, that delta px times delta x has to exceed h bar over 2, and that delta e times delta t has to exceed h bar over 2. What this tells us is that in any experiment where you try and measure position and momentum, the uncertainty in your position along x multiplied by your uncertainty in the measurement of the x component of the momentum, so the uncertainty in the momentum measurement times the uncertainty in the position measurement, will always exceed h bar over 2. So you cannot perfectly know position and momentum simultaneously. Additionally, in any experiment where you try and measure the energy of a system at a specific time, the uncertainty in the energy of the system multiplied by the uncertainty in the time when you took it is always going to exceed h bar over 2. And so, um, we will come to see this as uh, uh, as fundamentally important and also very different from how classical physics behave. So I am going to pause this here. As always, you guys are awesome. Have wonderful days. Thank you for stopping by. Don't be strangers. Enjoy your day, but not so much. Out to you tomorrow.